means sine squared of t plus cosine squared of t, which equals 1. And so the x, since it's equal to sine, would be x squared plus y squared equals 1. Therefore, you see from that circle center at the origin, radius 1. And things that look like this is a vector valued function, r of t equals x of ti plus y of tj. By the way, I could have made this a vector valued function, r of t equals sine of ti plus cosine of tj. It would have described the same circle, but it then would have been described as a vector valued function in r squared. This one is a vector valued function in r cubed, so you're used to that. But one thing I would tell you, notice one of the characteristics is only one parameter, t. I mean, x of t, y of t, z of t. The only one parameter is t. So the I component could be a function of t, the j component a function of t, and the k component a function of t. And when we make such a vector valued function, you may recall it's like a wire in three-dimensional space. So in this section, we're going to learn how to represent a surface, not a wire, but a surface in r cubed by a set of parametric equations. But what's different about the ones we're going to look at in this one is we're going to have two variables in our set of parametric equations. So instead of looking like r of t equals x of ti plus y of tj plus z of tk, in fact it will look like r uv is x of uv times I plus y of uv times j plus z of uv times k. And that will be called a parametric surface. And the equations, x equals x of u and v, y equals y of u and v, z equals z of u and v, are the parametric equations of that surface. So we can either represent it as a vector valued function with each of the components being a function of two variables, or we can represent it with a set of parametric equations. So that is what a parametric surface is, and let's have a look at one. The plot of the parametric surface r of uv equals f of uvi plus g of uvj plus h of uvk. I don't know why I have that capitalized, but I just fixed it. Is shown below, and here's our f, g, and h. See, I'm saying that f of uv is sine of u plus v, g of uv is cosine of u minus v, and h of uv is u plus v. So what does this thing look like? And the answer is, it's weird. This is the parametric surface described by these parametric equations. Now I don't have it written as a vector valued function. If I did, it'd be r of t equals sine of u plus vi plus cosine of u minus vj plus u plus v. Just for the sake of the argument, what would change if that was cosine of u plus v? I don't even know. Let's have a look. Why then, our vector valued function is back to being a wire again. So that isn't any fun. So let's go back and say, whoops, we meant that to be minus there, right? And now it's a parametric surface. And you might say, well, all right, well, what if we multiplied the u in there by 2u? And you know what? I'm going to keep that as a plus to see what's different about that one. The answer is, well, it's still a surface. It's a weird looking surface, but it's still a surface. Okay, that's the graph of it. So, right, well, what would be different then if I said maybe u minus 2v, right? And there would be that parametric surface. And what if I changed my h to, instead of u plus v, it was 2 plus v? Then I get this parametric surface. So, I mean, we can really play with these a lot. I'll try to do some examples after this one that make it have a bit more meaning. How about that one? Wowie. Look at that parametric surface. Just an amazing looking thing. Oh, that's worth writing down in my book of memories, huh? Wow, look at that one. Wow, look at that parametric surface. And we're, of course, only looking at a small portion of it. Looks like our u values go from -1 to 1, and so do our v values, right? So, fun with parametric surfaces, part 1.